I now call to order the Society's 2,439th meeting in the 150th year since its founding on March 13th, 1871. Good evening, everyone, and welcome to PSW Science's Spring 2021 meeting and lecture series. Because of COVID-19, the Society is bringing this meeting to you via Zoom from locations all around the world rather than our usual home, the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. Our speakers tonight are Simon Bennett and Dan Irwin of Crossrail Limited. They will be speaking about building the Elizabeth Line subway running across London, underneath some of the city's tallest buildings and some of its most historical areas. I'm Larry Milstein, President and Program Director of PSW Science, one of the oldest scientific societies of Washington, D.C., founded in 1871 as the Philosophical Society of Washington, to provide a forum to exchange scientific ideas, further scientific understanding, and encourage scientific inquiry. This lecture is being recorded and will be posted to the PSW Science YouTube channel, where it will join over 150 other recordings of PSW Science meetings and lectures. We invite you to explore these presentations and to become a member through the PSW Science website, www.pswscience.org. The Society is grateful for the sponsorship of the 2020-2021 lecture series by the Policy Studies Organization in cooperation with the American Public University and by a donor who has asked to remain anonymous. Please join me in thanking all of our sponsors. Before we turn to the lecture, in keeping with the Society's traditions, we will welcome new members and read the minutes of the previous meeting and the summary of the previous meeting's lecture. I am pleased to announce that the following members have been elected to the Society. Rita Maloff, a forensic advisor interested in criminology, molecular biology, and quantum physics, who learned of PSW from PSW member Carl Merrill. Simon Bennett and Dan Irwin, our speakers tonight, who learned of PSW through our invitation to them to give tonight's lecture, and whose interest will be clear in some small part from their presentations tonight. Please join me in welcoming them all to membership. Membership is the most important pillar of the Society. I encourage everyone with an interest in science to become a member. It's easy to do using the PSW Science website, www.pswscience.org. You'll find the blue Join button at the upper right-hand corner of the website homepage. PSW Science is a 501c3 charitable education and professional organization. Dues payments and other donations to PSW Science are tax deductible. Recording Secretary James Heelan will now read the minutes of the 2,438th meeting and the lecture by James Evans on building alien intelligences. James, the screen is yours.
Thank you, Larry. Good evening, everyone. On April 9th, 2021, by Zoom video conference broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2,438th meeting of the Society to order at 8:02 p.m. Eastern Daylight Time. He welcomed new members, and the recording secretary read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, James Evans, Professor of Sociology, Faculty Director of Computational Social Science, and Director of Knowledge Lab at the University of Chicago and the Santa Fe Institute. His lecture was titled, Designing Alien Artificial Intelligences, Programming Beyond the Limits of Human Knowledge and Reason. Evans began with a question. What kind of artificial intelligence do we want? Scientists in the 20th century established human intelligence as the standard by which AI was measured. Scientists programmed machines to play games like checkers and chess and measured their success by competing those machines against human players. Evans questioned whether continuing to target AI to human performance is the most efficient and ethical investment. Alternatively, in 1955, William Ashby first proposed AI as amplifying intelligence. Ashby and others posited that humans could augment their intelligence by minimizing the transaction cost between human thought and objectives. Instantiations of this concept include computer mice, file systems, and EEG helmets. Asking, is that all? The speaker described 21st century competitions, including the Netflix Algorithm Prize and international chess tournaments. Ensemble teams consistently won. The speaker then posited that science has advanced through abduction, the logic process formulated by Charles Sanders Peirce, by which hypotheses are based on surprising or theory-defying evidence. According to the speaker's research, the unpredictability of a scientific paper's conclusions predicts the likelihood of the paper receiving a major award like the Nobel Prize. The most predictive factor for unpredictable papers is the novelty of the scientific team's expedition from their area of expertise. Evans said, discovery occurs in conversation between insiders who identify familiar puzzles and outsiders who solve those puzzles with alien patterns. Evans is now working on whether scientists can create alien intelligences that increase the likelihood of major scientific discoveries. Regarding his research on the replicability of published pharmacology research, Evans said findings from decentralized communities using different methods, citing to different sources, are more likely to replicate. His analysis of clinical trial data produced similar results. Evans then proposed a new vision of AI as diverse or alien alternative intelligence. He envisions diverse intelligence coaches to guide humans into thinking about things in new ways, diverse intelligence collaborators to burst bubbles of certainty created by insular thinking, and diverse intelligence coordinators to assemble teams designed to facilitate collaboration. In 2019, Nature published a paper about unsupervised AI that studied material science literature and predicted forthcoming new materials with 40% precision. Evans said the AI was successful because it was not bound by the scientific community's accepted inferences and methodologies. He then described how his research team significantly improved a similar AI's success rate by giving it general guidelines to de-randomize its crawls. The team tested their enhanced AI on scientific literature for thermoelectricity, ferroelectricity, photovoltaics, pharmaceuticals, and SARS-CoV-2 vaccination agents. Their AI consistently replicated the inferences that human researchers ultimately reached to make scientific advancements, and predicted what teams would make those advancements. Algorithms considering author information were more accurate near-term from the prediction, while algorithms that did not consider author information were more accurate long-term. In sum, Evans said his research showed that to generate robust insight and rapidly advance technology, scientists need an ensemble of diverse intelligences, both human and AI. In that pursuit, scientists need to design alien intelligence that is not bound by the limits of human cognitive influences. However, he cautioned that scientists must be mindful of hybrid vigor, which requires a balance of both difference and recombinability between ensemble members. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein adjourned the meeting at 10:19 p.m. The temperature in Washington, D.C., 14 degrees Celsius. Weather, cloudy. Number of concurrent viewers on the Zoom and YouTube live stream, 91. And views on the PSW Science YouTube and Vimeo channels, 325. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. The minutes will be posted to the website in due course. Please send any corrections or comments on the minutes to corresponding secretary Robin Taylor at correspondingsec@psw.org. pswscience.org. A video of the lecture is available for everyone without charge on the PSW Science YouTube channel, the PSW Science Vimeo channel, and it can be accessed directly from the PSW Science website. We now turn to tonight's lecture. It's my pleasure to introduce tonight's speakers, Simon Bennett and Dan Irwin, who will be speaking to us about one of the largest infrastructure projects in Europe, construction of Crossrail, the new Elizabeth Line subway beneath London. And they are rather heroically speaking to us from London, where it is now well after 1 a.m. Simon Bennett is head of Learning Legacy at Crossrail. He is a civil engineer, transport planner, and communications professional. He worked on developing the original Crossrail London Underground scheme, and then worked on developing the project and securing powers for the undertaking. He led the consultation team and then the petitions negotiation team that saw the requisite bills through Parliament. Once construction began, Simon served as head of stakeholder engagement and then program community relations manager. Dan Irwin is geospatial lead at Crossrail. He leads development of geospatial solutions to integrate and support digital building information management systems for the construction of the project and to serve as the management backbone throughout its operational lifetime. Dan has worked throughout his career as a geospatial subject matter expert in sectors ranging from the environment, utilities, transport modeling, and construction through to asset and facilities management, all of which skills have been applied in Crossrail. All questions will be fielded in the Q&A session after the lecture. Simon, the screen is yours.
Thank you very much, Larry. I will now share my screen, share my presentation. Good evening, everybody. As Larry says, my name is Simon Bennett, and I'm currently Head of Learning Legacy at Crossrail, which I will talk about at the end of my presentation. Our two-hander structure will be that I will introduce the program, the project, and how we got to the construction process. Dan will then give you a rundown about the use of building information management on the project, and I will then finish with the work that we are in at the moment in bringing that railway into use and handing that over to the eventual operator. So in terms of an introduction to what Crossrail or the Elizabeth Line is, it is a new railway in the centre of London. On this map here shown in red and with the inset map, which joins the existing surface railways to the east and west of London through a new tunnel, 42 kilometres of tunnel, twin tunnel, which enable those trains which currently run into termini east and west of London to continue their journey through the centre of London and thereby increase the capacity of the central area. It runs east-west and it links a number of key areas of London, including Heathrow Airport, the new office area of Canary Wharf, and the West End and the main city of London, which are the grey areas shown. Railways below London have been around since the beginning of the Underground in 1863, built by Brunel as the Metropolitan Line. The first idea for national railway sized trains came about during towards the end of the Second World War, when the country was considering how to build out of the aftermath of the war. But that did not come to fruition until 1988, when a north-south route called Thameslink was opened. And then what? Well, we have the history of the Crossrail project. There was a study done by the the Department for Transport in 1989, which recommended a route east-west across London. And it had a life in Parliament from 1991 to 1994, when it fell and was not taken forward. It took until 2000 for it to be resurrected, and a company was set up called Cross London Rail Links in 2001. And at that point, I rejoined the organisation. We went through the process of creating a business case for the scheme in 2002, 2003. That was reviewed in 2004, and we finally got agreement to deposit a bill into Parliament in February 2005. It then took us until 2008 to get that authorisation to construct the project, and construction began in January 2009. We had the central section route already safeguarded, that being the blue line on this map. But we spent some time in 2002, 2003 looking at which routes on the surface would be the most advantageous. And we arrived at a preferred route, which is that which was subject to the Montague Review. The purpose of the railway, as I mentioned, is by providing that new capacity in the very centre of London, we create this impact on crowding on the existing underground. So in plenty of areas of London, we see an up to 30% decrease in crowding on the existing underground services. And along the central line, which we directly parallel in the very centre of London, over 30% decrease in crowding. Those are lines which were reaching their capacity and could not have continued to grow without a major scheme such as Crossrail. We also, by removing the need to change at those termini, massively decrease the journey times for key journeys within London. So from outside London to the west in Slough to Tottenham Court Road, that goes down from 55 minutes to 36 minutes. From Heathrow into the centre of London, that nearly halves as well. So these are some examples of the journey time savings, which add up to a significant benefit in our cost benefit analysis. We then went through the authorisation process after having passed that review. And the bill in Parliament involved authorisation of our works, giving us power as the nominated undertaker to undertake the works. There are a number of requirements on the project, though, known as the environmental minimum requirements, which we are required to comply with, including a construction code about how our contractors must behave during construction. A major part of the scheme is the acquisition of land, the vast majority of that being land below ground, but we do have the right to acquire that. But we have the station sites at the surface, which also needed to be acquired. And that was one of the powers that the bill gave us. And finally, in terms of local planning consent to the buildings that would be replaced, the buildings that we knocked down, that there were deemed permission for all of those developments was within the bill. However, the detail of those is still part of the local authorities' powers, and they have a thing called Schedule 7. So this picture is of us delivering the documentation to Parliament. That's the Houses of Parliament behind. We submitted the bill in February 2005, and it went through both Houses of Parliament. Select committees in the House of Commons heard 466 petitions on the original bill. We made additional provisions which attracted another 99 petitions, and it took until December 2007 for us to finish the process in the House of Commons. The process in the House of Lords was much faster. Only 113 petitions remained by that point, and we were finished in May 2008, which led in July 2008 to royal assent to the Crossrail Act. There is a reason why the scheme went ahead this time when it failed in the 1990s. One being that we already had our safeguarded route through the centre of London, and people were aware that the railway was coming. We were impacting urban and existing railway locations in comparison to other railway projects which have attracted a great deal more opposition because we're talking about building in locations that are already built up. The local authorities themselves would directly benefit from the new stations, so they were on board and positive about the scheme. The scheme had cross-party political support, and possibly most importantly, there was recently created the new Mayor of London with borrowing powers and powers to develop schemes of this nature and power to run Transport for London, the Transport Authority for London, which did not exist before. At the time that we were going through Parliament, the Mayor was mostly aligned with the national government in terms of political colour, and we were also in a very long economic boom. So it was, while these projects take a long time to develop, we were not subject to the previous scheme where the boom had finished and Parliament was unsure that railways would be needed in future. So then we had, once we had the Crossrail Act, we moved into the delivery process. Here are some of the things which show the size of the scheme and what we had to build below ground, including that 50 kilometres of track, 42 kilometres which is brand new in tunnel, large underground spaces, including a junction, and very large stations in comparison to the underground stations, 250 metres long and much wider and much larger overall than a typical underground station. In terms of governance, we are sponsored by both the Transport for London and the Department for Transport. So they have a joint sponsor team which sits above Crossrail and oversees it. Crossrail Limited has an independent board and an executive, and an operator which sits within Transport for London called Rail for London, who run the Elizabeth Line brand. When the project opens, it will be known as the Elizabeth Line. And in terms of funding, the reason why we have those two sponsors is that we have that the funding for the scheme comes from those two areas, the Department for Transport being the national government and TfL representing London government. TfL's funding of the scheme was 1.9 billion, but it was also responsible for one of the larger parts of the scheme with a business rate supplement, which is levied on businesses in London. And that will run into the 2030s. And that additional taxation of just under 2 pence in the pound on business rates is underwriting a 5.25 billion contribution from TfL to the construction of Crossrail. TfL, the DfT's direct funding is 4.8 billion, and there are other various strands, including the work on the national railway network, the existing surface routes, which is being done by Network Rail, of 2.3 billion. These numbers are based on the point at which we went into the scheme, and we have in fact bust this budget, and further work has been done between those organisations to fund the increase necessary to finish the railway, which I'll talk about at the end of the presentation. In terms of construction, the tunnels in the centre of London are the larger part of it, and these are the two methods of construction. We have a platform tunnel here, which is built by a sprayed concrete lining method, and we have a running tunnel, which is built by a tunnel boring machine erecting concrete rings behind it. We have almost as much platform tunnel in terms of length as we do running tunnel. The tunnel boring happened between 2012 and 2015 with 10 drives using 8 different tunnel boring machines. And these are the drives there, and we show pictures of the tunnel boring machines being launched below. In terms of construction of our platforms, once we had that sprayed concrete line tunnel that I showed before, that then has received a secondary lining and then a deck for the railway and a platform structure, which you see over here, some of which were cast in situ and some of which were brought in, built off-site and brought in. Then we assembled our platform edge screen door supports, and you see also here some of the supports for the overhead line electrification. Then at the back of the platform, we erected a cladding system and clad that, and resulted in stations which are much larger than an underground station, and with curving junctions between the adits and the platforms themselves. So here are some pictures of our stations in construction and what they will look like when completed. They are now largely at this stage. And as well as the stations, we shouldn't forget our shafts and portals, which are significant items of infrastructure in their own right. Here we have in the middle at the top Stepney Green ventilation shaft. We have ventilation shafts which are part of our station buildings, which will eventually be wrapped around with developments. And here we have a portal with one of our new class 3, 4, 5 trains coming out of it. So I'll now hand over to Dan to tell you about the building information modelling on the programme.
Thanks for that, Simon. I'm just going to share my screen now and we'll get into it. So what you should hopefully see, load it. Welcome. Thanks for that, Simon. My name is Dan Owen. So I have worked for Crossrail for about 10 years now, initially as a geospatial SME and latterly the lead on geospatial within the business. And what I'm going to talk to you about over the next half an hour or so is how we use building information modelling or management to help assist with the construction of this vast project across London. So the first thing I'll do is take you through an introduction of some of the challenges we faced, as well as what the history of building information looked like throughout the course of this project and how we had to adapt and evolve along with that. And then I'll take you through our common data environment. This is the framework and systems that we put in place to support a lot of the construction that went on. And you can see an example of some of the output of that on your right. This is showing how some of the construction sequencing would happen. And then lastly, I'll talk about some of the benefits, some of the things that worked for us, and some of the innovations that we used, as well as some of the lessons learned, some of the things that didn't go so well, and some future considerations for any future infrastructure projects that might come into play. So into the introduction. So first of all, challenges. One of the biggest challenges that Crossrail faced when building, constructing this railway was that we had to go under London, which is over 2,000 years old and as such has a very varied infrastructure buried underneath of it. What you can see in this slide here shows an example at Liverpool Street Station of the existing infrastructure that was already in place before Crossrail came in. And what you should see in the middle is the Crossrail station that was being built. And that included a post office tunnel that had to route straight through that. And what this doesn't show, and which actually was more prevalent as well, was all of the buried utilities, of which there were hundreds of kilometres of pipes and electrical cabling that had to be managed, as well as places like archaeology sites where we had to, be very wary of what we were trying to get involved with. Because of this, we had to be exceedingly accurate. The example here shows what was called threading the eye of the needle. So this was where one of the tunnel boring machines was passing through Tottenham Court Road Station, and the yellow that you can see here is the route that the TBM would take through the station. The blue above it are the foundation pilings of the station itself, and the red below is the platform for the Northern Line, which ran through that station. And the tolerances were exceedingly tight. The actual gap that we had between the tunnel boring machine and the foundation pilings above were about 50 centimetres. So we had about half a metre to spare and about 80 centimetres below. And because of this, we had to be exceedingly accurate with what we were doing. So much so that we actually developed our own custom coordinate system to minimize the linear distortion you get with certain projections when sort of dealing with this sort of stuff. And as opposed to a national coordinate system that we have in the UK where that distortion can be up to 400 millimeters over a kilometre, we got that down through the use of London Survey Grid in the central operating section to about 5 millimeters in some places. And so sure were they of the accuracy of this that when we actually came to doing the work, there was only a short pause in the use of that Northern Line below whilst we came through. But for the most part, it remained open. The next challenge we had was technical. We are trying to fit a 21st century railway into all of this. And we had to deal with a number of different systems from rolling stock through to systems, comms, fire safety, And all of this needed to be integrated to be able to talk to each other. And it was going to be a very complex build. And lastly, we had a contractual challenge. We had a program of work that encompassed around 50 projects at around 200 primary contractors. And all of those, we needed to be able to collaborate with ourselves and also with each other. So why use building information modeling? Essentially, there were a number of requirements here. We wanted to build a safe railway. We didn't want anyone to come any harm during the course of the build. We also wanted to build a world-class railway. We wanted something that was of the highest quality. As was mentioned earlier, we needed to be able to collaborate with our contractors and our clients in order to make that build happen. And of course, we wanted to reduce the costs and the time taken to complete that build. So just a brief history of Crossrail with building information modeling. Back in 2008, when Royal Assent was first given, building information modeling was a very new subject matter. It wasn't very widely known. And in the UK, at least, there was only one standard that applied to this, and that was known as BS 1192 Part 1. It had only come out the year before, but it talked about the use of collaborative workflows and common data environments to support construction industry. And as a result, what we started to build in 2008 onwards in terms of systems to help to manage this mammoth project, use that standard as a starting point. When we start to move into the design phase, we found that there were new standards starting to emerge. So we had PAS 1192 coming along Part 2 in around 2011, 2012, which was around the construction part of a building information model project. But we were already on the ground doing things. And so it was very difficult for us to just stop what we were doing and say, right, hang on a minute, there's a new standard come out, we need to go back and change everything. So we weren't really obliged to follow some of the things like organizational information requirements or employers' information requirements that are stated and listed out in that standard. What we did have as part of the contract that we would let is the works information. Now, this was a contractual document that we would give to our contractors, which told them what information, both digitally and physically, we were expecting to get back from them. And this followed very closely what the employer's information requirements set out. And then once we got into the construction phase, we started to see things like PAS 1192 Part 3 come in, which was more around the handover into operations and maintenance and standards around that. Unfortunately, again, we couldn't really stop what we were doing. What we did do is we tried to rationalize a lot of the data that we were creating in terms of what we would hand over to the operator to try and fit as best we could those standards as they emerged. So I'm going to talk now about our common data environment. What did we set up and how did we set it up? So primarily, the common data environment is really what our asset information model should be. These are the three primary data sets that are used to run the structure or the infrastructure project once it's commissioned. And this is broken down into three components. First, we have the graphical model. So this is in terms of what we produced, our computer-aided design models, our CAD, and also data that we would create through our geographic information system or our GIS. We also create non-graphical data, and primarily for us, this was about asset information. We were creating a lot of new assets, and all of those were going to have to be maintained once we open the railway. So the asset information was a primary focus. But as well as that, again, the GIS system holding both graphical and non-graphical data at the same time was a very important part of what we were doing. And then the third part was documentation. As good as a graphical model or non-graphical data can be, you still need documents to help to support that railway once it's in operations. That might be health safety files, operation manuals, and the like. And so we had an EDNS set up for that purpose. And the three of those together formed what we call the triumvirate of our common data environment. There were other components to this, and it wasn't just those three, but for the purpose of this, we're just going to focus on those. So we're going to look at the graphical model part first. So this was the CAD side of things, and what we went out and procured shortly after Royal Assent was given was a product called ProjectWise. This is a CAD design management tool which allowed us to centralize the design files that were being generated as part of this project. Latterly, we did also start using things like Synchro and SolidWorks to do some of the other stuff, which I'll come on to later. In total, we've produced so far, I think, about 4 million design files are loaded into that system, and is used by all of the contractors, both ourselves, the contractors, and they work with each other. Again, there are CAD standards around that. So we built a standard to ensure that all of the data that was being created consistently and to a certain quality. That included, for example, all of the design files being generated using our custom coordinate system, London Survey Grid, so that you could overlay two models from two different contractors and for them to fit perfectly. And we introduced a process that was in BS 1192, which was enable us to make sure that the right checks were being carried out on those design files as part of that process. This included CAD QA checks, engineering content checks, and specifically the interface coordination. We needed to make sure that one contract that might be doing civils wasn't impeding on the work that structural engineers were making, or that the MEP guys would be doing. And that sort of data would, again, would be all sorts of things, include civils, structural, architectural, mechanical, electrical, but also fire safety, track, and all sorts of other data sets. In terms of the GIS, we used a number of different tools over the course of the project, mostly from Bentley and Esri, and this included desktop, web, and mobile technologies. What you're seeing here is a blending of both the GIS data, or some of the GIS data that we had, with the CAD data, so that the model of the station here at Custom House was actually coming from the CAD models. There are about 30 or 40 CAD models there in the center there, and then we're actually using the GIS to show its surroundings and other data sets that were available within the GIS, and creating our own as well. So you can see here that the actual rooms, for example. Again, this did also have a number of standards associated with it. So we had a geographic information standard, data and metadata standards, as well as the coordinate system standard. And in total, there are about 57 work instructions that we created that would allow us to manage all of the various content that we were creating as part of this, from cradle to grave, in that sense. And some of those data sets included environmental data sets, geotechnical data sets, land survey, and topographical, and a whole host more. Again, these were just some of those. What you can see is us showing our points of interest, and we can actually go on and see the model in two different views now. So what we're actually going to do is show, we've actually loaded both the design, the original design for Custom House Station, and the final construction models. And you can see the difference between the two, what changed during the course of the design. What we can also then do is we can actually start to interrogate this. We can actually find information that we're looking for. And this is where the power of having the information behind these models really works. Here we're searching for lights. So this is finding us all of the lighting structures within that particular station. We can also search for doors, as I'm about to do, and see all of the doors in that station. Or we can be slightly more generic and just search for mechanical components. And what you're going to see next is all of the mechanical components within that station. So again, it made it very easy for users to actually interrogate and find what they're looking for. But we went beyond 3D as well. We did quite an awful lot in 4D modeling. And what this is applying those 3D models and linking it to the work schedule that we were carrying out things with. So there was a product called Primavera, which we used for our works management, and we linked in the 3D models and could apply that to create construction sequencing. And this could be done before we actually went on site and actually started to dig. So we could actually see what was going to happen before it would happen. And this allowed us to then understand the pitfalls and pick up any problems that might occur as a result of that, but also have a baseline to say what should be happening at that moment in time. We did something similar with the GIS, so we did some spatio-temporal analysis, and what this was about was actually understanding what was where and when. What this specifically was in relation to was we had sensors, hundreds of thousands of sensors across the work sites, which were monitoring particularly the movement of things as a result of the TBMs passing through. After they passed through, there was expected to be some settlement behind them, but also there was noise and vibration issues that might potentially have thrown themselves. And if claims came in subsequently, it allowed us to go back in time to review the sensors at that point in time when the damage was supposed to have occurred, to review the position of the TBM and anything else that might have been going on at that location, and to understand whether or not the claim was valid or not. So moving on to non-graphical data, we, as I mentioned, were trying to create an asset information system whilst we were moving through. Typically on construction projects in the past, we have found that asset information is collected either at the end of the project or not at all. And as a result, the operations and maintenance costs skyrocket because you don't know what's there, you don't know where things are, you don't know how they've been built. So we had to create about 600,000 assets, give or take. And we built a system, our asset information management system, actually inside of our document management system, which allowed us to actually relate documents to our assets as well. And this started off using Uniclass as a standard, although we found very early on that Uniclass didn't really work very well for rail. It was fine for buildings, but for rail infrastructure, it didn't work so well. And obviously, we were looking at things like ISO 55000 and PAS 1192 Part 3, which I mentioned earlier. And ultimately, what we created were our asset data dictionary definition documents. Apologies, it's a bit of a mouthful, which we called AD4s for that reason. And what these were a document for every single asset class that we were potentially creating, explaining exactly what attribution we needed to be associated with those assets, and how they should be collected, what they should look like. The process by which we developed our asset breakdown structure in the way we were storing things was hierarchical. So we would start with a primary functional unit for a given facility, for example, and this might be your drainage system, or it might be your lighting system, or it might be your fire safety system. And this encompassed all of the assets that fell within that. And then potentially, although not in all cases, we would then go down into a functional unit. So this would be a subsystem within that system. And finally, we would go down into the asset and equipment level. Now, the asset actually was defined not as a physical thing, but as a requirement. It is a requirement to fulfill a purpose at that location. So you might be in need of a drainage pump, for example, to stop water ingress. And as a result, you have an asset that is a drainage pump, and then you have a piece of equipment which you would put in place to fulfill that requirement. What it meant was that we could take the equipment piece out and replace it with a different piece of equipment if necessary, without having to remove the asset itself, because the requirement still existed. And we also were collecting non-graphical data through the GIS. As I mentioned, there were a whole different host of data sets that we would create, about 200 or 300 map layers in all. And again, we were using Esri and Oracle as a relational database behind all of this to host all of that data. And all in all, we produced about 400 million data features over the course of the project, and it's still ongoing to this day. But what we also did was we started being able to link our data sources. We saw earlier the 3D model that was inside of our GIS. We could link to that, but we could also link to our document management system, or our estates management system, or our master data model, which I'll come on to in a bit. The example here, this is an example from ProjectWise. This is a drawing that we have here. And if we zoom out a bit, what we should find is an equivalent structure inside the GIS, which has the same location code. What that meant is we could start attaching things to it. We could start creating relationships. We could actually start seeing those drawings inside the GIS and making them available through a single interface for users to be able to go and find them. And we could actually round trip the whole thing. You could go from ProjectWise to the GIS and back again, or you could open a PDF rendition of that document. And because most people didn't have a CAD software on their machines, but they did have a PDF reader. And so having a PDF made available to them and having those drawings made available to them made it much, much easier. And then finally, we come on to documentation. Again, we use Enterprise Bridge, which is a web-based tool for hosting documents. I think, again, at the moment, we have about 6 million documents in that system, covering a wide range of things. We use a number of different standards in order to build that. But ultimately, the process was that we would have central document controllers who would sit inside of Crossrail Limited, and they would manage site-based document managers that would be associated with the contractors and help them, assist them to create documents, to upload documents, to manage the documents within that system. But it was one system that everybody used. And again, the sorts of data that we're creating were health safety files, operation manuals, and also PDF renditions of drawings, as I mentioned, from the CAD system. But what Enterprise Bridge did, and what that system did as well, was not just document management. That was one strand of what it actually did. It was also managing our contracts, our asset breakdown structure, as we saw earlier when looking at our asset information. Our Crossrail management system, which essentially was where our standards were kept and where our other policies and procedures were stored. Our assurance reporting, our materials compliance, the list goes on. And lastly, I wanted to talk about the master data model. Now, this essentially underpins everything we've just talked about, or everything I've just talked about. It didn't exist at the beginning of the project, and it was realized fairly early on that we did have disparate systems. We had a document management system and a CAD system and a GIS system and other systems out there, but they weren't talking to each other. And because they weren't talking to each other, it meant that people were going off and naming things what they wanted to name them. There was no standard around naming conventions. There was no consistency around the naming conventions. And so this tool was built to help to manage that, to make sure that there was consistency between these different systems and act as an integration tool between them. It was a custom piece of software. It was built in-house, web-based. And essentially what happened was we had data owners. I myself was the data owner for the location part that you can see here. And this is where change would happen. If we had to change the code for something, a station or a shaft or a portal, we would change it in this location here. And then that would be our configuration management. And then the other systems would either have that pushed out to them or would pull it, depending on the system. But it meant that the systems were in sync and we could actually rely on the consistency. So that was our common data environment. We built all of this stuff, but how did it actually benefit Crossrail? Well, the first thing that it did was it gave us great visibility of design. We could actually understand what was happening out on site even before it started. As I mentioned, with the construction sequencing, it meant that we could actually understand what we were doing before we went out. It also meant that we had better management of that design. We could actually use that to do things like clash detection. Having those models, particularly the coordination models that were generated, it meant that we could cross-discipline check that to make sure that what someone was building from a civils perspective wasn't going to be impacted by something that an MEP engineer was going to be making. Again, we mentioned the automation of the CAD quality assurance, and what that meant was that people didn't have to worry about whether it fitted in terms of the the level naming conventions, the global positionings. That was all done as part of that quality assurance. And that meant that the data had integrity. It meant that people trusted it. It meant that they actually understood that everything was going to be of that same quality. And it also meant that we could apply better resource management. Again, with something like the construction sequencing, we could see exactly what was going to happen, and we knew what was needed and when, both in terms of material, in people, and in time. And we understood the physical environment better. We go back to the example of the TBMs passing through the grounds, and actually knowing where all of these buried structures were before we started that piece of work meant that we could do a lot of work to overcome those challenges before we ran into them. And it also meant that we had greater performance analysis capability. It meant that we could actually analyze where we said we would be at a given moment in time against where we actually were. And you'll see this in the next slide in terms of our innovations. So we had a whole series, there was a whole program called Innovating, which actually looked at using innovations to help Crossrail. The first of which, I'm just going to pick on a few here, the first of which was a Bluetooth low energy beacons. One of the big problems we had when you were out on site is that you couldn't geolocate yourself when you were using a mobile device. So we put in Bluetooth low energy beacons to help that geolocation. And this became particularly useful when we started looking at augmented reality. This was something that we actually took those 4D models that we were producing and put them onto mobile devices and put them out on site. So actually what you could do is you could actually overlay the 4D model at a given moment in time, and this is where we should have been in terms of the construction, and relay that against what was actually being built. So we could do that performance analysis on site. We also played with virtual reality. Here is an example of an app that was put together that again took those models and that information that we were collecting throughout the course of the project and made it very accessible to users to be able to walk around the station and understand the station, which is very useful for the station operators and maintainers to actually be able to familiarize themselves with the stations before they were even ready to be used. And we also did on-site document verification. Traditionally, what would happen is that there would be someone would go on site with a document relating to a piece of work that they would undertake, and it might be a hard copy or it might be a PDF that they've downloaded onto their device. But quite often, it wasn't the right version, that it had changed since they had looked at it. And having this app on your phone, you could simply scan a QR code and it would check and tell you whether or not you were using the right version of the document. And if you weren't, it would give you the option to take you to the correct version to use. We also implemented virtual information structures. Again, this was more around our asset information, but the way that it was designed using object-oriented design of that data meant that we could repackage it to fit a different purpose. When we collected the information, it was very contractor-centric. We had contracts and they would deliver back asset information to us. But when we want to hand over to the operator or maintainer, they're not really interested in the contractor perspective. They're interested in the operations perspective that is more facility-based. And having these virtual information structures in place meant that we could recontainerize that information and package it in a way that could be accepted by the people we were handing over to. We also use smart boards, particularly during design reviews. So once we got to a certain part of the design lifecycle, there would be a design review carried out, and we would have smart boards in the room with the coordination models loaded up, which people could interact with in the room, rather than having sheets of paper or flat sort of documents to work from. They could actually interact with that model and understand it far more intuitively than they could by other means. And it was very useful in helping to move those design reviews along and to eliminate more risk. And then there was the use of mobile GIS, which we started using sort of halfway through the project. And primarily what we used this for was for data gathering exercises whilst out on site, but particularly for managing our site boundaries. we had a number of construction sites around London, and we had to be very careful about the hoarding that we placed around those to make sure it was in the right place. What we didn't want was hoarding being placed where it shouldn't and trespassing on land that wasn't ours, or conversely, not putting hoarding where we should, where we were responsible for any accidents that might happen. So we used the mobile GIS to allow users on site to actually see where the hoardings were or where they should be to geolocate themselves and figure out whether or not they were actually in the right place. So in terms of benefits realization, as I mentioned at the beginning of this, there were a number of sort of reasons why we wanted to use building information modeling. The first of which was safety. Here you can see an example at Westbourne Park, which is just west of the underground section. And what we had to do was create an elevated bus deck to allow us to work around what was the traditional bus deck, which was going to get in the way of the construction. Because we were able to do this 4D modeling, this construction sequencing, it meant that we could improve our understanding of how it was being done, and we could eliminate any mistakes before they occurred in terms of the sequencing that was going to happen, that we didn't have people in the wrong place at the wrong time. And it also demonstrated that we were able and ready to dig. Because of this as well, we had an improvement in quality. Again, the use of the coordination and the interoperability of data between these different data sources, and the fact that they were integrated, it meant that the quality of the data was higher. We could go back and do rework at a very early stage to eliminate problems that we might find with the design. And it also improved the temporal quality. What I mean by that is it improved the construction sequencing, so that we could eliminate any duplication of efforts and reduce any overlap that we might find between two events that might be taking place at the same time. And then lastly, there was collaboration. So this, having this central set of tools that was available to everybody, both Crossrail and contractor alike, meant that we had just one system for managing it. It reduced the overhead for us. Rather than having to have a separate system for every contract, we just had the one system that was central, and it reduced the overhead on managing that. And it made it access easier. You know, people knew that there were only 2 or 3 systems that you had to access to get to what you needed. And in some cases, like through the GIS, you could actually go into that one system and actually find the information in those other systems directly. In terms of some specific cost and time savings, there are a number of different things we did with CAD that helped us with what we were doing. And on average, we were looking at about 31 person days a month per contract were being saved because of these tools. It reduced the repetition of tasks. We automated a lot of things to reduce that repetition that would be happening. And it just made things happen much, much more smoothly. From the GIS perspective, again, the intelligent design and the integration of the GIS with the CAD improved the early planning in particular. There was a retrospective analysis done of some of the work that was carried out on the design of the actual routes, and we found that because of what we'd done with both the CAD and GIS integration, we were saving about 5,000 hours a year worth of rework that would otherwise had to have been done. Most people were finding about a 15% decrease in the time it took to find things, because of they could go through a single spatial platform, which made things easier to find. In the case of the estates management team, which was looking at the occupation and ownership of the sites during the construction, they found that they actually reduced the time it took them to create and manage that information by 75%. And it saved them about £120,000 per year. From a modeling perspective, we've already seen many examples of that construction sequencing. At Farringdon Station, we created a 3D model and linked it to the delivery program. It cost us money to create, you know, that did cost us £120,000 to put together. But what it did do is it managed to reduce our risk contingency by 8 million, because we were able to prove that we were ready and that there were no issues that we would run into during that construction. And then lastly, there was asset information management. Now, we weren't going to save any money. creating asset information. As I said before, mostly asset information is collected at the end or not at all. So anything we were doing during the project was going to cost. However, if we didn't collect that information, it was forecast that the costs of operation and maintenance of the railway afterwards would increase by up to 20 to 25%. Now, bear in mind, we've been at this for 10 years, and the operational lifespan of Crossrail is estimated at 120 years. So when you start to look at the savings you can make, which worked out to be about 44 million a year by having this information up front and extend that out over 20 or 40 years, you now find yourself looking at savings of 800 to 1.7 billion pounds. But it wasn't all plain sailing. You can see in this example here, there were some issues throughout the course of the project. It wasn't, it wasn't just a wonderful thing. In this example here, it did transpire that, as I understand it, the technical drawings didn't follow the standards that we put in place, and that's why we had the issues that we had. But we did also have some early contract issues. Some of the contracts were let before we had these systems in place. And I guess the lesson learned here is that what was given back to us wasn't fit for purpose for what we needed it for. And we've had to do a lot of rework to get that back in place, and we're still paying the price now. We also found, because we had these big centralized systems, we started to suffer from vendor and even version lock-in. It was very difficult once we were in using a particular piece of software to actually go off and use something else. And even to the extent where we couldn't even change versions of the software, and we started to lag behind as the project continued to deliver, and the software would become out of support. We also found that some software that was being developed more from an IT and technology perspective rather than what was actually needed on the ground. And as a result, we did see some cost spiral in terms of what was being developed, and what was being developed didn't necessarily fit what we needed. One example of something that we tried to do very early on, as one of the first contracts that was let, was the development of a common object model library. So what this is a set of common components which you can then share. This might be signaling equipment or track or doors or whatever it might be. And the idea was, if we could create that, then it would reduce the time that each of our contractors would have to spend on creating those themselves. Unfortunately, this is back in 2008, 2009, and it was a step too far for us. We really shouldn't have expected that to work. The systems in place were not good enough to be able to do that, and it never delivered. We also found that data interoperability was an issue. I mean, I've talked about all of these systems being in place that were talking to each other, and that is true. They did, but behind the scenes, there was a lot of moving of data from one place to another. We didn't really achieve true interoperability because a lot of the systems didn't allow for that. And what we instead had to do was do extract, transform, load operations to move data between those systems, most of which were automated, so that we didn't have to worry too much about it. But that interoperability is still an issue to this day. We still haven't really cracked that one. And then lastly, there's handover. We are, as Simon mentioned, handing over to RFL, who are Rail for London, who are going to be the operator and maintainer of this. And I think there was an issue with the client expectation management. I think they were expecting maybe something more than we were going to provide, or in some cases less. And certainly some of the systems that they have in place can't support some of the stuff we've developed. Some of these amazing models and sequences that you've seen here can't be run by them on their systems. And so, although it was great for Crossrail to have developed them and has helped us, that sort of thing is not something we can really hand over. So, just in terms of future considerations to wrap up, if we could go back and do it all again, and I'm surely to hope we wouldn't, one of the first things we do is probably look at requirements. We needed to establish them as early as possible, and as I mentioned, where we didn't do that early enough, we saw issues, and understand what the client wants more. There was some disparity between what we thought the client wanted and what the client actually wanted. So getting a clear understanding of those requirements much earlier in the process would have helped us an awful lot more. And in terms of the asset classification as well, that really was key to understanding what assets we were going to be building and what assets we were going to hand over. In terms of data configuration management, we became a very data-centric organization. Historically, I don't think construction projects have ever created this much content as part of the project. And although we created a lot of data, and I've talked about, quality assurance and model reviews and everything else that went with that, we maybe didn't treat that data as the valuable resource that it actually is. Going forwards into operations and maintenance, we're going to find more and more that data is going to drive our maintenance regimes. Certainly the use of relational data models from the start would have helped save us more money. And then lastly, people. Ultimately, this is all about people. People are the ones that are creating this content. People are the ones that are using this content. And so people have a way of doing things. And I think that more could be done to make people aware of why we do what we do and influence their behaviours and outcomes. We did create something called the Crossrail Information Academy, of which you can see an example on the right here. And that was something where we got all of the Crossrail people in, all of the tier 1 contractors in, to explain to them why this was important, why it was useful, why it benefited both us and them to go down this route. And hopefully that is something that is a legacy that will persist beyond the end of this project. And that is me. So I'm going to stop sharing and hand back to Simon now.
Thank you, Dan. So I'll now wrap up about where we are currently on the programme and the last phases of the scheme. So Dan's talked a bit about the railway systems that we have, and that has been the major challenge and probably the reason why the line has not yet opened and is in fact not on schedule anymore. We have a huge amount of railway systems, not just track and electrification, but obviously the tunnel lighting, radio systems, etc. And the sheer amount of this and the amount of documentation and assurance and making sure that it all worked together ended up being, I think, more of a challenge than was understood at the early parts of the program. And I think a good reason for that is that it is a smaller part of the total cost of the scheme in comparison to the tunnelling, which is very expensive, but actually turned out to be relatively easy. So the focus gets put on that part of the program, which is very expensive, and the bits that are less expensive perhaps were left in a way that they shouldn't have been. So we have the tunnel systems. We also had to have our track installation, and here I wanted to talk specifically about the types of track that we used. Here we see a track being installed in the running tunnels in the normal way, which is bringing it in as panels and then concreting it in. But we also had floating slab track, which is cast into a resilient substrate that reduces the amount of vibration and therefore noise and referred vibration into buildings above. There are a couple of areas in London where there are significant receptors which are very sensitive. That would be in Soho, just south of Oxford Street, where a lot of our film studios and recording studios are. Throughout that whole area, we were required to use floating slab track. And very particularly under the Barbican Concert Hall in the City of London, we actually were required to provide a very specific type of track, which was actually on springs rather than a resilient pad. And that was phenomenally expensive and actually ended up being way beyond what was necessary to protect the concert hall above. So were we to do that again, we would probably have worked with the city to have just standard floating track slab instead. We have the station systems, and the big issue of our systems has been the systems integration, making sure that all of these systems work together, and particularly where there is the interface between the running railway and the station. So the train is the point at which those link together. And the key part is the signalling system. We are running a new system in the centre of London, that's shown here in the green signalling, which is cab-based train control. But it is connecting to those surface railways I talked about, and those have existing Network Rail conventional signalling. And there are two different styles of that. In the east, we have original style Network Rail conventional system with automatic warning system and track protection and warning system type signalling. In the west, however, we have European Train Control System Level 2, and the train has to be able to operate in each of those systems and hand over at the points at which it moves from one into the other. And getting that software right such that the train can talk to each of those signaling systems, and then when it pulls into a station that it can talk to the station systems so the platform edge doors are controlled with the train, has been one of the biggest challenges on the programme, and is one of the reasons why we have spent several years now beyond the time at which we were expected to open. This is our train, a Class 345 built by Bombardier in Derby in the UK, but a Canadian company has since been sold to Alstom. And as you see on the right, it's a metro style train. While it's a National Railway size train with overhead line electrification, different to the tube, it does have a continuous walkway all the way through the carriages, and the vast majority of the seating is longitudinal on the side, so creating a great deal of standing space, so that in that central section of London it can have the highest possible capacity. These trains are air conditioned, which is a new thing for the tube. Most people who use the Underground will know that every other line on the Underground is not air conditioned, and they are much longer and larger than the sorts of trains that we have at the moment. Those surface sections are, while a smaller part of the scheme, were also important to the project, and they required upgrading, in some cases providing electrification, overhead line electrification, and rebuilding of stations to lengthen them for the longer trains and to provide new ticket halls. And some of these pictures here show our new flyover that we had to build so that the tracks into Heathrow had a second route, which is this area here. This is Ilford Station, and this is Acton Main Line Station. This is the new station building, and this is the old one. So you can see that we're building significantly larger stations to cater for the numbers of people that we expect to use the new railway. So we are now in our commissioning and handover phase. We've handed over 2 stations, Custom House and Farringdon, to Transport for London, and are in the very last stages of Tottenham Court Road as we speak. Throughout this year, all the central section stations except Bond Street will be handed over. So here we see some finished stations, a platform level at Tottenham Court Road and the station concourse at Farringdon. And we are moving from dynamic testing, which is up until quite recently, we've been testing the trains in tunnels in motion, that's dynamic testing. We're now moving into trial running. So we have changed from being a construction site on which trains can be run to do testing to a railway on which we have to get permission to finish the construction. So we are now an operating railway. While not carrying passengers, we run on the same rules the existing railways do. So we have our route control centre at Romford here, which is managing the infrastructure. So throughout this year, we will be handing over to Transport for London Rail. TfL Rail are already operating services to the east and the west into Liverpool Street to build up the reliability of those new trains. And they, in some cases, they started out as a 7-car unit and are now being built up to the full 9-car, full-length trains. So here we have one of our trains in Heathrow Station and again at Romford. So the opening phases for the scheme, we already have delivered the stages 1, 2A and 5A. These numbers are out of sequence now because of the fact the project is delayed from its original opening date. But the really key part is the stage where we open the central section. So that is stage 3. That's expected to be open in the first half of 2022, and we'll be running trains then from Abbey Wood through to Paddington through that central section. However, we will essentially have 3 separate railways. We'll have the existing line into Paddington High Level, the existing line in the east to Liverpool Street High Level, and the central section. We'll bring the whole thing together in the following year, throughout 22 or into early 2023. Certainly by the end of 22 is the plan, so that we will then have the full 24 train per hour service in the central section in the peaks. A decision was made that the line, when open and when operating, would be known as the Elizabeth line, and we announced that 5 years ago now, 4 years ago, and this is the Queen receiving the plaque when the renaming happened. I'd just like to take a few slides now to talk about our sustainability story, because there are a couple of things that I think are particularly important about the way we approach the project. We have looked at the carbon impact of the project, and based on the predictions at the beginning of the scheme, we've delivered a reduction of 11% against the carbon that was expected to be embodied in the project. And we've done several other important things, including using the excavated material from our tunnelling to create a new wetland habitat out towards the east, more or less in the Thames estuary, a little bit round the coast, on a piece of land which was reclaimed, where the seawall has been breached and the excavated material from Crossrail has been used to create bunds. This is going to create a new wetland habitat for birds, for the Royal Society for the Protection of Birds. And then one of the areas which people are always particularly interested in is the archaeology. In some cases, we're obviously building stations. The tunnel boring machines go below the level of any human interaction with the ground. But at station sites, we were in some cases digging into roads which had not been dug over many times. So at Liverpool Street, and that's the top right here, you can see the burial ground for the Bedlam Hospital. And there were 3,000 skeletons here which needed to be exhumed. And in the end, we were running that archaeological site 24/7 to get it done before the work was needed to start. And then on the left there, you can see the excavation of the Brunel engine sheds to the west of Paddington Station, with a picture of that above it. So you can see that this was originally a broad gauge engine shed, and then it was changed to standard gauge, for those of you who are railway geeks and understand those things. And finally, this is the work that I now do, the Crossrail Learning Legacy. We work with the professional institutions in the UK and with our successor major projects to collate the work which we have done and create papers based on our experience. And this presentation, I think, is an example of that, where we want to share what we have done so that others can learn from it, take what we've done that is good, and learn from where we could have done things better. So we have a Crossrail Learning Legacy website, and I'd recommend anybody going to look at that and looking at the 12 themes within that and anything that would interest them in terms of how a major project is built. So that's the end of the presentation, and I think I'll now pass over to Larry, who will manage the questions. Thank you.
Thank you, Simon and Dan, for a very interesting talk on a very large project of interest to all of us here and throughout the world. So we have time for the Q&As. Zoom participants can raise their Zoom hand or type their question in the Zoom Q&A panel. I will call on Zoom participants in turn to unmute their mic and ask their question. Zoom participants who decide they don't want to ask their question aloud, they can just write that they don't want to ask their question out loud, and I will read their question. YouTube viewers can text questions in the YouTube chat box. All text questions will be read aloud so everybody can hear them, and they will be recorded and heard on the video recording. So we'll start with Frederica Durema. Frederica is a PSW member, and she was formerly head of the Air Force Laboratory of Research. Frederica.
Yes, good evening. Thank you very much, both speakers, for an outstanding kind of presentation of an outstanding project. And as a physicist and a computational scientist, I, in a sense, saw a proof that such a project could not have been possible without the information technology that you used. So I asked a question early on when you talked about 4 million design files, and I kind of asked what was the size of the data, and I know that there were multiple sets of data. And then, you know, I wanted to also, in relation to that, ask, you also used computational modeling, finite element methods, and what computational resources you used for that. Then you talked about instrumentation and sensing, and certainly that is for the design cycle, but also at the operational cycle, because you talked about how you want to develop methods so that the maintenance, in a sense, does not become, you know, both the static and the old, but more dynamic and real-time and continuous kind of test and evaluation. So can you speak a little bit about these issues, how you address them and how you include them in the project? Daniel, maybe.
Yeah. In terms of the size of the design files, I mean, obviously each file varied in size depending on what was in it.
Yeah.
We're talking terabytes of data here. Each file would be separated into its own unique space and would be versioned as well. So we might have 15 or 16 versions of a given design file as it evolved throughout the project. But yeah, I don't know the exact number, but I know it was terabytes of data that we were storing and are storing to this date. In terms of the use of the sensors and how they were used throughout the construction project, most of those were dismantled around, I don't know exactly, it was about 2016, Simon? Can you remember exactly when?
Talking specifically about the monitoring of buildings, I can talk about that.
Yeah. Yeah, I mean, those are the ones I'm sort of
There's
thinking
two
of.
sides to this question. There's the temporary works, the temporary monitoring that we did during the works, and then there's the sensors and data and remote sensing that we have in what we've built, so that the IM can use it. And I know there is some of that. I'll talk about. I can talk about the tunnel monitoring. The purpose for this was obviously we were predicting ground settlement above our tunnels, and also particularly above where our excavations were happening from the surface. So in some cases we had dozens of automatic total stations on buildings around the at surface level, with prisms erected all over the place. So these were real-time monitoring the movement of buildings, so that when if movement was above a certain threshold, alarms would go off. There was the ability to increase the amount of compensation grout being pumped into the ground between the tunneling and the surface to push the buildings back up. And as a result of that, we had very few damage claims because our compensation grouting was pretty effective. But it did require us to take areas of surface land that we wouldn't otherwise have had to create those compounds for the compensation grouting. We dismantled all of that very quickly inside a year after the tunneling completed, and we moved to a satellite interferometry method of managing the long-term settlement of ground. here you're well within the sort of 10 millimeters that happens as a result of seasonal change anyway, but we wanted to keep an eye on it, and we wanted to make sure that we were able to defend claims that came after. So there's a very useful, good paper on learning legacy about use of the satellite imagery to manage our settlement from there on, after that temporary monitoring was taken down.
Yeah, no, I mean, I was going to say the INSAR satellite monitoring is the primary method now by which we keep track of that settlement, potential for settlement that might be occurring. In terms of sort of going forward into operations and maintenance and sensors for managing that, there are a variety of different sensors on the track. We also have a number of onboard sensors on some of the trains, both the passenger trains and some yellow plant, which can run the tracks and actually automatically check for track defects or other issues that might occur. And they're going through their testing phases at the moment. I think they'll be sort of rolled out fairly soon. Does that answer the questions?
I think we'll take a question from Phil Nicholson and then a question from Giovanni. Phil? Philip? You have to unmute.
Hey, I was working, I'm a geotechnical engineer. I was working on the Boston Big Dig, which was about $15 billion. And also in Toronto, with a 28 kilometers of a subway. I wonder, what was the soil investigation? Was it clay, rock, or what was the water table?
All of the above.
All together. And the second question I have, was the station built before tunneling or after tunneling? Or during the tunnel?
Right. So I think I can answer both of those, and the answer to both of those questions is both. Is manifold. So when talking about geotechnics, the vast majority of Crossrail's tunnels are in clay. They're in London clay. It's quite a homogeneous medium. It's extremely easy to dig, particularly when you're at tunnel boring machine level, which is between 17 and 25 meters below ground, which is quite a long way down. In terms of encountering things like sand lenses and water in the ground, there are only a couple of areas where that was an issue in the central area, and Farringdon is the main one because Farringdon has a significant number of faults in it. Yeah. It's also the area where the Fleet River runs. There's again papers on the learning legacy about this, and I'm not a geotechnical engineer, but I know them well. So building Farringdon station was quite difficult, but the really lucky part of that was that Farringdon station largely sat below Smithfield Market, which was one single structure, and it had an underground car park. So we had the ability to take over significant parts of that car park and use it for compensation grouting. The compensation grouting which was undertaken at Farringdon was phenomenally extensive, and it was all obviously real time. So that was managed relatively well. There were a couple of other places, particularly at the western end of Liverpool Street Station on the escalator incline up to Moorgate Station, where we encountered a thing called a drift-filled hollow, which was where silt had fallen, had been washed into an area below the surface, and that ended up needing ground freezing as well as compensation.
Yes, we did that. Yes, that's good. Thank you.
Yeah. And then the second part is sorry, and then the other part of the other type of significant ground there was chalk and waterlogged chalk, where we were tunneling under the River Thames. So we had two different types of tunnel boring machines. The vast majority of it was in the clay, but we had slurry machines running under the River Thames, and the chalk came out very wet, needed to be dried out before it was taken away. So that didn't go to the Wallasey Island wetland habitat that I talked about. That was the question about the geotechnics. I've forgotten the second question already.
Thank you very much.
The second question.
Yeah, the second question was about the station that were built before the tunnel or after.
Some of them before and some of them after. It was based on where the station appeared in the drive. So with Canary Wharf, there was the opportunity to build the box for the station first. Yeah. The tunnel boring machine then broke through that box and was tracked through it and carried on. But in the west, we were digging the tunnel first and then broke that out. So at Paddington, for example, the tunnel boring machines came through first before the box station had reached that level, and then those rings had to be broken out. So it depended on where it was in the drive.
Good. Thank you very much. Very interesting.
Good night.
Thank you. Philip, I guess you can speak now.
Yep. Thank you very much, gentlemen, for a very interesting talk, and I appreciate you staying up this late to give it. I had a fairly simple question. You mentioned the clearance in some cases for the tunnels was as little as 50 centimeters from neighboring structures, and that you needed millimeter accuracy mapping. So for the mapping, I understand, but how did you keep track of the positions of the TBMs themselves while they were doing their work? I imagine 20 meters is too deep for GPS satellite systems to work.
Yes, as I understand it, the main way of checking, because obviously the TBM has a reckoner of how far it's gone, and so what you're really doing is checking the accuracy of that, is that you set up a set of prisms and reflectors back down the tunnel, and you extend the survey grid via laser survey equipment instruments to take you right back out to the tunnel entrance to a known point.
So it's kind of old-fashioned surveying, but with lasers and things.
Yes.
Yes.
Yeah.
And if I could, a somewhat related question. I remember reading somewhere in one of the Crossrail brochures that the tunnel boring machines were in fact left in place at the end of the project. They were dug off into side tunnels and they were not disassembled and brought out again. I just wondered what was the reason for that. They must be phenomenally expensive pieces of equipment.
I love this question. 2 of the shields were buried, but most of them weren't. So we had 8 TBMs, as I mentioned. 6 of those were recovered in their entirety. The only 2 which were buried were the 2 which came from the east into Farringdon. And the reason for that was that they arrived at the station at the point that the station had already been finished. So they couldn't be popped out into the station there was no way of removing them. The ones that had come from the west could be. But the bit that you bury is just the shield. It's sort of essentially the first 10 meters and the cutter head. Now the cutter head is a sacrificial thing anyway, really. Its teeth are being replaced all the time. So by the time it arrives there, its life expired. The can is only about, the first 10 meters is not the most expensive bit of the machine. All the guts of the machine, all the train, everything that hangs out the back where the segments are brought in, the conveyor for the excavator material to go out, and obviously the cab and everything that's inside the TBM shield where all the electronics is, all of that's recovered and taken back out the tunnel all the way to where it started. So in terms of the total cost of a TBM, you're recovering, I would say, 80% of it.
Okay, that makes much more sense. Thank you. I feel better. Thank you again.
Okay, we have a question from a YouTube viewer, Jorge Aponte. How does digitization improve cost and efficiency of the Crossrail project? And I think that's partly in your slides, but maybe you could go over it briefly again. And then he asks, how has the pandemic affected the design of the spaces within the rail line? Are there any new tools, systems that were used in this project you could highlight in that regard? And did the pandemic have an effect on how you design the air ducts and the ventilation? And if it didn't in this project, how do you think it would affect the future project?
Yes, so the first part of the question, obviously, I can have a crack at. So yeah, I mean, the use of creating all of the information that we did, as I said, was it allowed us to understand what we were going to do before we did it, so that we could then proved that what we were going to do wasn't going to cause any problems. We weren't going to encounter any clashes, any risks. We weren't going to run into infrastructure that was buried in the ground that we didn't know about, and that would improve the actual time, or reduce the time it would take to do these tasks, whilst doing it more safely and more efficiently. I mean, ultimately, that's what it was all about. I mean, some says, like I said, the collection of the asset information, it's not going to benefit us in terms of the construction, but obviously, once you move into operations and maintenance with the information they've got, it's going to make it much easier to manage that railway going forwards.
To the second part of the question, basically it hasn't, because we were designed and finished before COVID-19 hit. It's affected obviously our construction, but we stood down for a very short period of time, and then because of the stage we were at in the program, we're able to get back up and running quite quickly and exercise social distancing on sites and work with the right protective equipment. But in terms of the design, it's happened too late for us to change the design of the program, as the railway, as a result. It may change the way it operates. That's something for Rail for London to consider in terms of making space on the trains. So unfortunately, I can't answer that question really. But yeah, I'm sure the next railway after us is considering that very, very, very much.
Jorge's in Colombia, and he had a comment on YouTube about the construction of a underground in Bogota. I wondered if you had had any conversations with anybody or there. I think it's being built by Chinese government assistance.
That's a very interesting point, because what has happened...
I'm sorry, it's not an underground, it's an elevated, but...
Yeah. The Department for Transport has an organisation called Crossrail International, which is trying to use the positive experience of the early stages of the programme, particularly in terms of setting up the scheme, to be an export ambassadorship for the UK, and Bogota is one of the systems, and the Colombian government is one that Crossrail International is already working with.
Yeah, that was another question. So there is an international effort to capitalize on what you have developed and learned.
Yes, I mean, it's a separate organisation of Crossrail itself, but people that were involved in Crossrail are part of it. And it's building connections all over the world, particularly in Australia, actually.
Is there any attempt by Crossrail to monetize what the software tools you've developed?
No, because
on a goodwill nonprofit.
Yeah, no, we're essentially we're a government company, so that's not. We will cease to exist probably the year after next. What we've built gets passed on to the future schemes within the government major projects portfolio.
Is all of the software and the source code public domain?
Oh, well, I don't think so, but that stands.
No, most of what we did was using proprietary software. A lot of this stuff, we didn't build the software ourselves. We just used existing software that was out there and customized or configured it to our needs. Some of the vendors will have taken some of the development tasks that we did within their software and taken it away and reused it for other purposes. But that's not something that we would have been involved with.
PSW member David Rabinowitz asked, with the massive web-based database, were there any attempts by outside entities to infiltrate the system? What kind of security systems were used, and how early in the project were they implemented?
I'm not sure I could answer that one. I've not seen anything about any infiltration or attempted infiltration of our systems, whether that's because it hasn't occurred or whether I just don't know about it. We have standard IT security in place to prevent access from outside. And a lot of the stuff we built sat inside of our network. So you would have to get through our firewalls in order to get to it in the first place. There have been attempts at phishing and spam operations against us, but I don't think anything serious. I don't know if you know of anything more than that, Simon.
I'm afraid not. You're outside our area of expertise there, I'm afraid.
Yeah, certainly, like I said, a lot of stuff was hosted by us, and therefore it was within our purview to manage and maintain and protect it. And we had a third-party IT support agency that would help us with that.
Yeah, I imagine the fear would be corrupting the information in a way that would be dangerous for the operation of the system.
Yeah, but obviously,
Designs and things like that.
Yeah, I mean, as part of a standard IT infrastructure, obviously we would have had backups, and we had failover sites where we could fall back on if there were any issues with corruption of data. So it wasn't as if it was just existed once, and if that went, we were lost. We could have switched over to backup facilities.
Al Ehrlich has a question, PSW member. Al?
Yeah, I was wondering, I know nothing about the geology of the London area. Is it sedimentary rock or granite? And to what extent is the design that you folks use dependent on this? I imagine those different kinds of substrate have different strengths, different not optical, sonic properties, sound absorption, and so on. So for starters, what's the soil like underneath London?
As I say, for the vast majority of it, it is clay, and it's quite a dense and homogeneous clay, and that is just the absolute best possible medium to dig with a tunnel boring machine. And it's what makes the sprayed concrete lined platform tunnels easy to do as well, because you can excavate it and it holds itself up until the sprayed concrete that you spray up goes off and holds the clay back. It's not rock, so it doesn't require blasting, and it's not sand, gravel, chalk, things which have once you've excavated them create greater amounts of settlement and don't hold themselves up. And so it's extremely easy to dig through, and it's also quite in terms of the noise and vibration. The amount, the depth at which we were digging our tunnel, and the way that we build the railway and the resilient track, and even the standard track is quite absorbing of vibration, means that it was unlikely to be a massive problem anyway. So yeah, ideal is basically the answer.
But it sounds like the strength of the tunnel and the strength of the interstitials between your tunnel and other structures that are pre-existing depend on your concrete, right? There's nothing, clay isn't very strong, I don't think, is it?
Well, it does. It's much more incompressible than sand and gravel.
Okay, thank you very much.
So Bruce Murray has a question, I think partially answered in your last part of the talk, Simon, but go ahead, Bruce.
I just wondered if you ran across any interesting archaeological ruins, or maybe even a few paleontological things while you were digging.
We did, in fact. I wouldn't say much of it was massively unexpected, because London's quite well known and quite well archaeologically mapped as it is. So we brought in the Museum of London Archaeology Service as our overall archaeological contractor. And we do huge desk studies before we start. For example, we knew that the Bedlam burial ground was there at Liverpool Street. What we didn't know was quite how many bodies there would be. We did find two quite interesting paleontological finds. One was in the dock at Canary Wharf, which was a mammoth bone. And we also found a bit of prehistoric amber, but without any mosquitoes, so we couldn't pull a Jurassic Park.
Were you, for the most part, was your digging mostly too far down to run into those sorts of things?
Yeah, the running tunnels and the platform tunnels are 17 to 25 meters. And really the human impact on the ground is absolutely in the top 3 meters. Obviously, modern buildings have foundations which go deeper, but for the vast majority of the history of London, no one's digging deeper than about 3 meters below ground. So our station sites, we did have archaeology, but actually at most of our station sites, we were knocking down buildings that were already there and rebuilding them. So that ground had already been churned over many times. So it was only the places where we were digging into completely new ground, for example, Stepney Green, where we found the remains of an old manor house, Liverpool Street, because that Bedlam Hospital, that station is actually in a road rather than on the site of an existing building. At Tottenham Court Road, we found the remains of a factory that was a jam factory, but we knew that jam factory was going to be there. We just weren't expecting the sheer number of broken jam pots from the sort of 1800s through to the early 1900s.
Was there any jam left?
No. There is actually, and I think it may still be online, an interactive tour of the archaeology of the project, which was done with the Museum of London in Docklands. And I might be able to find a link, and you can share that with people, because that's quite.
That would be great. We'll put it up
good.
on
It was a very good exhibition.
the minutes. So there's a couple more questions. One is actually mine. I was wondering why you chose overhead electrification versus third rail systems that are used in, for instance, New York and here in DC.
Yeah. Well, mainly because it's an existing national railway service for most of its length. And in both sides of London, except for the very last bit from Heathrow out to Reading, it already had overhead line electrification. So if we had to go third rail, we would have had to re-electrify those bits.
Okay.
So what we're really doing is extending that overhead line into the center. An overhead line is better anyway because it's less lossy because it operates at a higher voltage. It's also safer because it's out of reach.
And how portable is the BIMS system that you put together to other infrastructure projects? Would basically they have to recode and recustomize, or could they take your shell and start plugging their own data into it? Assuming that follows your standards.
Yeah, again, so these were for the most part proprietary software. So you could take the stuff that we had and you could plug it into another project very easily. And we were already seeing that. There's another project called High Speed 2, which is another big rail infrastructure project, which is taking off and starting to build now, going sort of from London up through Birmingham to Manchester. And that is already using a lot of the same stuff that we did. And there's already been a lot of lessons learned passed over to them about how they manage their data and their asset information in particular. So yeah, there's nothing that they would have to do particularly differently from us. And I think, to be honest, the software has evolved since we started using it. As I mentioned, some of the software we're using now is quite old, and actually there's better software out there to do the job than what we're using. But it's just this project's been going for 10 years.
Theoretically better.
Yeah.
I just upgraded a 64-bit operating system and application programs, and my computer's running about 50% slower. Thanks to Microsoft and Apple. Anyway, we have a last question here from James Van Artstelem, which I'll read. James says, you described tunneling with narrow tolerances between existing structures. I'm surprised that extremely precise data exists on old buildings so that you can determine exactly where the footings are. What's the nature of these databases? What entity owns and manages them? How is data acquired on very old buildings? And he says, great presentation, thank you.
Okay. Probably we may have been, what's the word? We may have created an expectation there that might not be the case. The threading the eye of the needle was between the infrastructure above we'd just built. So that was ours. The Northern Line, obviously London Underground has a very good idea of where its tunnels are. They're well surveyed. So specifically for that issue, we had very good data about where the assets were in the ground. Elsewhere, there were certainly cases where we didn't know, but as I said before, for the vast majority of our tunneling, we are a long way below ground. The buildings that we had to avoid because the foundations were as deep as the railway are very, very modern buildings. They're the ones which are the tallest, and therefore we know where they are because we can find as-built for those. The landowners are the ones that hold those records, but so do the local authorities. So when you do the desk study, you go to the local authority and you can go back to the planning applications for particularly the large buildings which have quite most recently been built in London. So for example, at Canary Wharf, our station is inside one of the docks that was left from when Docklands was redeveloped. So it avoids all the piled foundations of the very large buildings that have been built in the area. And so we are basically in a pile-free area. We did, however, find some inclined piles, which we weren't expecting, which were the footings for the original dock cranes. We thought all those piles for the foundations for the cranes went straight down, but we found some inclined ones and had to cut them out. Luckily, of course, the cranes were no longer there, so they weren't holding anything up. So you just, TBM hits metal sleeve of a pile, you stop, back it off, and go in and cut it out, and then start again. Can I think of any other examples? We did hit a well. We hit a well at Tottenham Court Road, which we weren't expecting because it wasn't charted. But the first you know about that is the bricks are coming out of the tunnel boring machine and it's gone. Luckily, it had already been capped at a higher level, so it didn't cause any problems at ground level.
It's very interesting. It's a pleasure to have you two to talk about this. You have obviously an encyclopedic knowledge of the software and the actual construction. And I thank you very, very much for staying up this late and for presenting this this overview of the project. So you both have a rain check to come when you're in DC, if you ever get over here, to come and join PSW at the Cosmos Club for dinner, reception, and a lecture if you're interested. And even if it's not on a day that's convenient when we're having a lecture, we'll arrange something as a small token of thanks for spending the time with us and putting together this presentation. So I really appreciate it, and I think I'll let you guys get some sleep.
Yeah. It's been a pleasure.
Thank you. Thanks for having us.
Good night.
Good night.
Thank you, everyone, for joining us. The recording of tonight's lecture will be available to everyone on the PSW YouTube channel and in due course on Vimeo and via the PSW website. Please share the links with your friends. And subscribe to the channel for notification on new postings. And don't hesitate to join. It's easy to apply for membership using the join button on the PSW website homepage. And please keep in mind that we have fared through this year of COVID fairly well, but new memberships have not been at the level of past years. And I would urge all PSW members to seek out others who might like to be members. And those of you who enjoy PSW on YouTube and are not members, to please join. It's really important for PSW to keep up its membership and to expand its membership. So thank you. Before you go, some closing announcements. First of all, the next meeting, number 2440, will be on May 7th. The speaker will be Tony Tyson, Distinguished Professor of Astronomy at UC Davis and chief scientist at the Rubin Large Synoptic Survey Telescope Observatory. He will be speaking about the potential impacts of satellite constellations like SpaceX's Starlink on astronomical observations and on ways to mitigate these adverse effects. The 2,431st meeting will be on May 21. The speaker will be Bill Powell of the State University of New York College of Environmental Sciences and Forestry. He will be speaking about the chestnut blight and approaches to bringing back a blight-resistant American chestnut tree. The 2,442nd meeting will be on June 4th and will feature the annual Joseph Henry Lecture. The speaker will be Carlo Rovelli, director of the Quantum Gravity Group at the Center for Theoretical Physics in Marseille, France, and distinguished visiting research chair at the Perimeter Institute. He will be speaking on quantum gravity. The 2,443rd meeting, capstoning the spring lecture series, will be on June 18th. The speaker will be Steve Stitch, program manager of NASA's Commercial Crew Program. He will be speaking on the U.S. Commercial Crew Program and human spaceflight. Changes to the spring lecture series, should there be any, and lectures coming this fall will be posted to the PSW website. Check there often for updates. And with that, before you go, please join me in thanking tonight's crew, James, Ann, Robin, and Cameo, for producing tonight's event. I will now adjourn the 2,439th meeting of the Society in its 150th year. I wish everyone a good evening. The meeting is adjourned.